Okay, so here, let's see here. They should be able to see me. Let's see. Good morning, everyone. I hope you can hear me. Um, I've received a lot of recordings for the Zoom cloud. Remember, every time that we have a uh, virtual class, the actual lecture will be recorded so that you can utilize that recording later to review certain items that we discuss. And it's certainly a utility for you to utilize throughout the term. I hope everybody can hear me well. Zoom has made some improvements this semester, so this is really good. Hopefully you've been able to check out the Blackboard site. The Blackboard site will cover everything that we need in terms of announcements and deadlines. And the nice thing is that your WebAssign is connected directly to the Blackboard. So you can go to Blackboard and click on the WebAssign tab and have direct access to that. Remember, everything that you have for your supplies and needs for this course have already been covered. We have an Open Books Plus section. And so if you get a little pop-up that says, oh, trial period for WebAssign, just ignore it. It takes a few days during the term for everything to kind of work out. Um, I noticed that everybody has their microphone on mute. I just want to make sure that everybody can hear me. If you can hear me, just drop me a message or, well, no, I'll just say this. Let me just pick out someone. Yarlene, can you drop me a message to let me know that you can hear my voice? That way I'll know that everybody has a good uh, audio going on.
Yes, I can hear your voice.
Wonderful, wonderful. Well, see, this is excellent because one nice thing about Zoom is that, like I say, from last term, the software has improved greatly. You can hear my accent much more vividly than the students could in the fall semester. But I want to welcome everyone to pre-calculus. This will be a good class for you, a challenging class for you, but basically a course that will prepare you for calculus. And when I mean that, the items that we study and review in this class, you will use often in the calculus. The unfortunate thing is that you're not always sure when you're going to have to use a certain topic. But I want to make sure that when you get to calculus, you have good preparation. Now, um, I will have office hours every day of the week, and I will send out invitations today, even though they may be a little bit choppy. I'm going to be compiling an email list for all of my students during the week, but I will send out invitations for office hours every day of the week. So if you want to go ahead and meet with me virtually, again, this is in basically a setup to ask questions. If you have a problem that you've already worked on, if you have a question about WebAssign, if you have a question about Blackboard or anything, the office hours last term were very useful. I certainly had many students that utilized the office hours quite often. And since you're on a schedule with your virtual setting here, I tend to think that more of you will take advantage of the office hours. So again, welcome to the class. And I'm not going to be a tyrant about attendance. I will always make sure that you have done your work, that when I check Blackboard and I checked WebAssign, that you are staying current with your work. I'm not here to police you. You're all adults, and I do want you to attend class, and I do want you to be a participant. But again, I understand that things do occur at times, and I will hold you to the responsibility of making sure that you keep your deadlines and stay abreast of all the announcements that occur on Blackboard. Now, what I want to do today, the first week will be a basic algebra review. Some of you might think, well, this seems like Algebra 2 in high school. Some of you might think, well, this seems just like college algebra. So what I want to do is to start with basically a word problem just to get everybody warmed up. And I will share my screen. I have a nice document cam. So let me do that. Okay. And like I say, with the new improvements to Zoom, all of the pictures are so much more clear. I can already tell this term, and so I'm excited about that. So let me just go ahead, everyone, and read this problem. This is basically a fraction of work problem, and I thought it might be a good way just to get everybody warmed up. Um, Again, you have utilized techniques to solve these problems in some of your previous classes. And so what I wanted to do is just give us an opportunity to work through an example and just maybe think about some of the ideas that we've done before. Now, let me read the problem. This is a classical exercise. We have a main pump here. Notice that empties oil tanker in 4 hours. So again, the main pump can complete the job in 4 hours. So we're going to say the job is emptying the oil tanker. And then the second portion here, the auxiliary pump empties the oil tanker in 11 hours. Okay, so we have 4 hours, 11 hours. Clearly, the auxiliary pump, a smaller pump, takes much longer to complete the job. Okay, now how does this work into the problem? Here's what we're told. If the main pump is started at 9 a.m., then determine the start time for the auxiliary pump to complete the job by 12 p.m. Now, again, there's been so much conversation these days about algebra and how it plays a role in the education of, our high school students and all individuals for that matter. And certainly there are times when maybe algebra would not be as beneficial to certain students in other disciplines. But of course, you all are in STEM fields. You want to become STEM professionals. So algebra is kind of one of those important things that we have to do. So when you read the news articles about changing math, remember that doesn't apply to you. You're in the STEM field, and so you're kind of stuck with the algebra and the trig. So I think that's always interesting to read how everybody wants to bypass the standard mathematics. And it's okay if you're not in STEM. Okay, now in order to do this problem, I just want to give you Professor Ron's way of looking at this that may be a little bit different from what you've done in the past. So we're going to write down main pump. And I'm just going to paraphrase. I'm going to say job in 4 hours. Now with the job in 4 hours, we can reciprocate and say 1/4 of the job per hour. That's the fraction of work per unit time. That's why we call these problems fraction of work, or maybe you've called them something similar to that. The auxiliary pump will say job in 11 hours. And so if we reciprocate that, we'll get the fraction of work per unit time, 1/11th of the job per hour. Now, one thing that's interesting here is that we see that the main pump is started at 9 o'clock and the job must be completed by noon. So we automatically know how long the main pump will have to run. Clearly, it would need some help. It's going to run for 3 hours. And if it takes 4 hours for the main pump to do the job alone, it's going to need help from the auxiliary pump. So at least this problem is worth our attention. So what we can see here, ladies and gentlemen, is that we don't know the time or the running time for the auxiliary pump. So what we can do is let T equal running time. And you can use whatever letters you like, it just whatever is convenient. Running time for auxiliary pump. And I'm just abbreviating here, AP for auxiliary pump. And feel free to do that. So now what we can do is say, okay, the total job is 100%. And this is what I actually did my first semester at San Jac when I actually had to teach some academic and college prep courses. I devised these techniques to help my intermediate algebra students. And so what I told them is said that the complete job or 100% of the job is represented by the number 1. And so that's always going to be the right-hand side of the equation. And so we'll have a contribution from the main pump and we'll have a contribution from the auxiliary pump. So this reciprocation here makes the problem a little bit more understandable in terms of explanation. So for instance, for the main pump, we have 1/4 of the job per unit time, and it runs for 3 hours. So that gives the fraction contributed by the main pump. We see that's 3/4. So you can already see that 1/4 will be contributed by the auxiliary pump. So now 1/11 fraction of the job per unit time times T, the unknown time. So even though this equation is very simple, it utilizes a lot of the techniques that we've learned in algebra, which is the symbolic computation. We use symbols to represent what we mean mathematically, and we try to let the symbols do most of the work because we're lazy, or at least we don't want to work so hard if the algebra can help us out. So now, if you like, you can take the equation away from the blanks. So we have 3/4. And then, of course, we have T/11. And this equals 1. Lots of times when I draw a 1, I'll put a little base on it so you can see that it's a 1 and not an L. But that really is more for emphasis. Now we can see that we've got a fractional problem where we want to clear denominators. We can see that the common denominator is 4 times 11. So we can multiply through by that integer to clear denominators. So just like we were solving equations in algebra to clear denominators, the same technique that you've done many times. Now we can see through symbolic computation, the 4s absorb. I don't usually use the word cancel. I'll say absorb instead and try to avoid a lot of slash lines just because that kind of gets in the way of your work. So the 4s absorb and we have 3 times 11. We can go ahead and multiply that out. That's simple. That just gives us 33. Or you can leave things factored. Oftentimes we'll just leave things factored to keep things simple. And then of course, The 11s here will absorb, and that will leave us with a 4 times a t. And then, of course, over here, we're just left with a 4 times 11 or 44. Again, the numbers are really simple, so we don't always have to leave them factored. Factoring will often allow us to absorb factors to keep our arithmetic simple. Now we've got a very, very simple equation. Notice if we subtract 33 from 44, we get 11. So equivalently, we have 4t equals 11. And now simply divide by 4. T is equal to 11 over 4. And of course, this is in hours. Now, if you like, you can go ahead and write this as a mixed number. 4 will divide 11 2 times with a remainder of 3. So this gives us 2 3/4 hours. Again, even if the numbers don't work out beautifully, it doesn't mean that the problem isn't any good. It's just nice to have nice numbers. And let me retire my here we go. Let me open this back up. I have to retire my email because it dings so loud. Santa Claus was good to me. I got a new Dell all-in-one computer for Christmas, and it works maybe too well. Okay, now let's complete the problem. Notice, if you like, we need the start time. So we have to think of working backwards. But notice this number is really good. We have 3/4 hours. Basically, 3/4 of 60 minutes will give us 45 minutes. So this just gives us 2 hours, 45 minutes. And so what we want to do is we want to complete the job exactly at noon. So we can just reverse time starting at noon. And of course, 2 hours will take us to 10 o'clock, and then another 45 minutes will take us to 9:15. So we have to start that auxiliary pump pretty quickly if we want the job to be completed by noon. So the conclusion would be, this is kind of like what you'll be doing with your WebAssign. Start auxiliary pump at 9:15. So again, problems like this maybe don't occur that often. You know, as you become a STEM professional, you'll be doing a lot of deductive reasoning as engineers, computer scientists. Some of you will be graphic designers. Some of you will be mathematicians working for an insurance company, all kinds of different jobs. And maybe this particular problem won't be something that you'll actually need to work. But the types of deductive reasoning exercises tend to be very helpful. And that's really why we do these things. Now, again, what I wanted to do with this problem is just to show you that we take very simple steps to solve problems. Every step is important. Unfortunately, we'll work a problem, and then for the last couple of steps, we'll get sloppy and we miss the problem. And we're like, well, wait a minute, I did the hard part correctly. Well, see, that's one thing I want to help you with. I want to make sure that you look at every aspect of the problem as being important. That is, as we work through these exercises, we think about what we're doing and we check our arithmetic. And one technique we're going to say more about today is clearing denominators. Even if we had variables in the denominator, this technique would work. And again, we want to minimize the amount of arithmetic by using factoring techniques, number theoretic concerns that will keep us from having to do excessive arithmetic. Again, that's called symbolic computation. And in some cases, ladies and gentlemen, this might be a little bit new to you, but again, what I want to do is introduce to you some new techniques. I don't want you just to see things that you've seen before. I want you to be able to acquire some new techniques. Now, one thing that is very good about algebra and important to what we do, especially when we move through the pre-calculus into calculus, is factoring techniques. Now, what I've done here is I have written down from your textbook some important factoring formulas and product formulas. And then when you look at this, the nice thing about the IPEVO here is that I can always check the focus. So now, here, let me move this keyboard up a little bit. I just wanted to make a couple of comments here. The nice thing about your WebAssign is that it has a really nice ebook, and the ebook covers the entire course, the entire book. And so when you look in your assignments, it'll say read these sections. Now, I'm not requiring you to read through every section completely. You know, look at the examples and look for definitions that are new. You also have SmartPen videos, which you may use. Now, since you have the virtual lecture, you may not use those as much as the students who do not have the virtual lecture. But the SmartPen videos are, again, Professor Ron working on examples, some that you may see me do in class in the virtual setting. Now, what I wanted to note here, again, you can find all of these in your ebook, is that when you look at all of these examples here, 2 through 5 in the first set are basically just special occurrences of the binomial theorem. You're thinking, okay, well, these aren't so bad. You're taking a binomial here, a plus b and a minus b, and you're squaring it. And here you're taking a binomial a plus b and an a minus b, and you're cubing it. So what I wanted to do was just remind you of these very important product formulas. Now, the very first one, again, if you wrote it in reverse, you would call it a difference of squares, but we have a plus b times a minus b, again, which is a very convenient formula that occurs quite often in algebra and mathematics. But when you think about, for instance, 2, 3, 4, and 5, you're thinking these are like shortcut formulas, so to speak. At the end of the class, we will complete study of the binomial theorem before you get to the more generalized version in Calculus 2. But this, again, is a shortcut method, because when you think of it, let's just look at a plus b. So when we square that, we're thinking, well, really, what does that mean? Well, that just means in terms of our symbols, a plus b times a plus b. Now, of course, we can always do this, but if the power gets larger and larger, it's nice to have a formula, and this will actually be something we see with the binomial theorem later in the class. But we wouldn't want to have to go ahead and multiply all of this out and collect the terms. Maybe it would be nice to already know the actual formula. So now when we look at this, if we just use the distributive law, we have a times a. That gives us a squared. And then we have a times b. This gives us an ab. And then we have a b times an a, just using the distributive law, ba. And then we have a b times b, or b squared. Now, one thing we know and we enjoy about real numbers is that they commute. Oh, complex numbers also compute. Imaginary numbers, they commute. So BA and AB would be equivalent. So we could just write BA is excuse me, A times B, and have two of these to add together. So let me write this down. So this is just a little extra step here, which is very clear, harder to explain than just to write. So now, again, using commutativity, we have two copies of AB. So this gives us A squared plus 2AB plus B squared. Now, one nice thing about this formula is that it's easy to remember, and we often find ourselves making careless mistakes when we omit the so-called middle term, so to speak, or the inner term. Again, when you square a binomial, you have this inner term, which we often forget. Now, of course, with the minus here, the plus 2AB term becomes the minus 2AB. And then, of course, for the cubes here, we can do the same type of analysis. That is, we can do A minus B quantity cube. And what I wanted to do, again, in your WebAssign, you're going to have lots of examples where you can practice collecting terms. And so I wanted to prove some of these formulas to give you an opportunity to practice collecting terms. So let's look at the third one, or actually the number 5 one. Let's just go ahead and verify this. Now, one thing that we notice, and it doesn't matter, we can leave the minus or write it as plus a negative, but this will be simple. So let's just go ahead and prove this formula by the standard technique. So we have A minus B times A minus B. So what we can do in this particular case is we can group the first two occurrences of A minus B together and then multiply by the third occurrence of A minus B. All right. And so now, notice here, this is just the formula A minus B quantity squared. So we can go ahead and use the formula we already know. This is just A minus B quantity squared. So we can go ahead and use the formula from here, number 3, that we already know. So this will give us A squared minus 2AB plus B squared. Again, using the property of the real numbers, the negative times the negative, the two additive inverses in product give us the positive, and then multiply by A minus B. Now, again, we can do the same thing. We can use the distributive law. So since it's a little simpler here, let's multiply each of these terms in the first set of parentheses by A. And then we can write everything in alphabetical order if you like. So we get A cubed. Now we have a minus 2A squared B using our laws of exponents, and then A B squared. Again, just collecting terms using our laws of exponents and just writing in alphabetical order. Again, using the fact that real numbers commute. Now let's multiply each of these terms by the negative B. So we get a negative A squared B. Now we have the negative negative. So we get plus 2A B squared. And then again, we have the negative times the positive. So this will be the negative B cubed. Now, notice when we do these types of calculations, we now want to put all the like terms together. So notice these are by themselves, so to speak. And then we have the A squared B term. We've got one here, and we have one here. And then we have the AB squared term, one here and 1 here, the like terms, so to speak. So now we have a cubed, and then we can just descend with the powers of a. We've got a -2 copy here and a -1 copy here. So we have minus 3a squared b. So we have these. We've taken care of these. And now the ab squared term, we have 1 copy here, 2 copies here. So we've taken care of that and that. And then the very last term, again, which is the term, the cube of the b term with a minus. Now, this isn't very glamorous. I mean, when you think about it, when it comes to collecting terms, it's just bookkeeping, but it's important bookkeeping. And now we're thinking, well, there's a nice pattern here. We wouldn't want to have to do this every time we want to cube an a minus b or a binomial. That takes a lot of work. And so what we can notice here is we've got a pattern with the coefficients of 1, 3, 3, 1, so to speak. And then of course this negative occurring because we have an a minus b instead of an a plus b. And notice the powers always add to 3, 3, 2 plus 1, 1 plus 2, 3. So these are patterns that we're going to notice in the generalized binomial theorem. Again, not very glamorous, but certainly very useful. We'll have many opportunities to use the a plus b quantity squared, a minus b quantity squared. We'll have many opportunities to use the a plus b and the a minus b quantity cubed. These will come up often in our work in algebra, as you remember in college algebra, and also in our work in trigonometry, when we have powers of cosines and sines with the power reducing formulas. So the algebra here, even though again seems very dry and maybe not the most fun to do, is extremely important just in terms of bookkeeping. So let's look at it that way and not look at this as something that's not worth our time. Again, this type of technique, though seemingly unimportant, is an important part of doing any math problem. So remember that all steps are important. Unfortunately, we knock ourselves on the noggin sometimes thinking, well, you know, I didn't pay attention to that step and I missed the problem. And so we're always having to be vigilant about steps that we think are very simple. Now, what you can see here, and again, you're thinking, well, it looks like we've turned some of these problems around and we don't really have anything new. And that is very true, at least for the first 3. So notice when you think of these in a factoring type formula, you're thinking of a sum of terms, so to speak, written as a product or as a product of factors. So of course, the difference of squares, our friend, a squared minus b squared, is the a plus b times the a minus b. Again, very simple to prove. Remember what we call these, ladies and gentlemen, are identities. These are all identities. These are equations that are true for all values of the variables for which they are defined. So notice here, I've just said that a and b can be complex numbers or they can be algebraic expressions. No need to discriminate against imaginary numbers. Remember, the complex numbers include everything. They include the fractions, the integers, the irrational numbers, the imaginary numbers. So when you say complex, you're having the largest umbrella that covers all the numbers. We don't necessarily mean that if a number is complex, that it has an imaginary part. 2 is a complex number. The real numbers are contained in the field that contains the imaginary number. So complex is just a way of encompassing all the types of numbers we deal with. Now, again, the perfect square, which I'm going to talk about in a factoring scheme in a few minutes, again, is just taking the binomial theorem and running it backwards. So we can say, oh, if we have the a squared plus 2ab plus b squared, that's just the binomial theorem identity, so to speak. So looking at it this way is a little bit different. Going here to here, we automatically think what we just did. But now we have to be a little bit more vigilant and say, oh, I've got two squares and then I've got this middle term, the minus 2ab. Oh, that's a perfect square. These are hard to spot when you move in this direction. Often we'll overlook the perfect square because we're usually thinking in this direction, starting here and going this way. So just remember, as you look at these, and you think about the direction, they can hold much algebra for you. And then when we think about solving equations, we like products. We like the zero product law, which allows us to set each factor to zero as long as we have a right-hand side of zero. Now, another thing that we'll talk about too, that at least with the cubic cases, comes into quite a handy situation when we're solving equations. Now, of course, these can be extended, but they don't tend to be as useful as the powers get larger and larger, because then, of course, the polynomial equations get extremely difficult to solve. So past the cubic here, we don't say much about these. But one of these, and of course, the fifth one, 4 and 5, you talked about in college algebra. The first one, number 4, being the difference of cubes. Again, this is not the binomial theorem. This is a difference of cubes. And notice these formulas are very simple. Again, can be proven the same way by collecting terms. That is, we have a minus b factor times the quadratic factor, a squared plus ab plus b squared. And then, of course, if we have the sum of cubes, we just have interchange of these two signs here. That is, the a cubed plus b cubed becomes a plus b times the quantity a squared minus ab plus b squared. So when it comes to these formulas, again, you have seen them before, but we just want to make sure that we have them, on the tip of our brains so that when we need them, we can utilize them and we can depend on them. Now, one example from one of your homework exercises had to do with a area calculation and factoring. So I want to talk about that. Again, you will enjoy doing some of these problems with your WebAssign that just give you some good practice. Now, here's what we have in our WebAssign problem. This is a simple factoring problem. What we have is a square within a square. A square within a square. So just go ahead and draw this. Again, all those nice identities you can find in your ebook. And of course, in the formula sheets that you'll see on your Blackboard site. Now, here's what we're given here. That is, notice here, this is what we call the unmowed portion. So this is like a habitat. Unmowed to make a better habitat for the animals that live there. And we're given that the edge of the outer square has a measurement B units. And then the way this unmowed portion square is situated, it's right in the center. That is, we'll have the same distance x from this edge to the corresponding edge throughout. So the problem's set up so that we have the middle square or the inner square centered in the larger square such that we have this geometry. Okay, and now the border, so to speak, is mowed. I guess I should make sure that's a W, unmoved. There we go. Mode. So the interesting thing about this is that, say you're working on the grounds committee, and maybe you have someone working with you that wants to solve this algebra problem, and this is what the problem's going to be. It says prove. The first part we'll call this A, and then we'll do A and rewrite A using some other techniques. Now, here this says prove that the mode area is, in this case, b squared minus b minus 2x quantity squared. Okay. Well, of course, my WebAssign just logged out. When you have the new computer, you got to change some of your settings. Now you're thinking, well, that's not too bad. So if we wanted to find the area of the mode portion here, then we'd have the larger square area minus the smaller square area to get what's remaining, to get the border, so to speak. So we would say area equals larger square area minus smaller square area. And so now, if you like, we can go ahead and do just some labeling here. Notice here that for the edge of the smaller square, we've got the B where we've subtracted 2 copies of X. So the edge here will simply be B minus 2 copies of X. I always say 2 copies or 3 copies. We keep track of things by figuring out how many we have of them. Even though that's very simple, it's important. So we're thinking, okay, well, again, B minus 2x, B minus 2x all throughout. And so to get the area of a square, we just square the edge. So the larger square area will be B squared. And then, of course, the smaller square area will just be the edge squared, B minus 2x squared. So that wasn't very difficult. You're thinking, okay, well, maybe you didn't need Professor Ron to do that. Now, here's the B part. Show the area from part A is, and this is a factoring formula, is actually 4x times B minus X. Okay. So when you look at this, you're thinking, all right, okay, I must need to factor things. And again, there are many ways to do these types of problems. There's no one set way. So we can take this particular expression and show that it's actually equivalent to this. But again, we can think of this as a difference of two squares and maybe make our life a lot easier. So now b squared, so this is where we get to use some of our factoring formulas. And the WebAssign actually walks you through this example. I just like to go ahead and work through this to give you one perception of it. And then with the WebAssign, you get to fill in the blanks. And again, be careful as you type in your WebAssign using the palettes for the fractions and the radicals and things, so you have an exact response. You'll get plenty of practice with that. But again, it's important to be able to type the good mathematics, just like you're writing the answer on a test. So notice here, we have a square minus a square, difference of two squares. So let's write this in the factor form. So now we have b minus b minus 2x. So that's the first term squared, b is squared, and the b minus 2x is squared. So we have b minus 2x times b plus b minus 2x. The idea is we square the b and we square the b minus 2x and we take the difference. And so now the unsquared parts will be the b and the b minus 2x. And here we subtract them and here we add them. And now we just collect terms. So using the difference of squares formula makes this problem very straightforward. So now let's go ahead and distribute the negative sign. So we have b minus b, and then minus minus plus 2x. And then of course here we can distribute the plus. We have b plus b plus a negative 2x minus 2x. And now, of course, these are additive inverses. They absorb each other. So we get 2x. And here we have 2 copies of b and 2 copies of the negative x, which if you want, you can go ahead and factor, but I'll go ahead and write it out for now. Then we'll factor it in the second step. So we want to make sure we get this, but so now we can see if we factor the 2, that'll leave us with the b minus x. So now we have 2x times 2 times b minus x. And now, of course, the 2 times the 2 will give us the 4. Again, very simple, but very illuminating. 4x times b minus x. Now, even though this problem is very simple, it does at least give us an opportunity to practice factoring in a symbolic sense. Factoring, as you well know from your science work, you'll take more science and physics and chemistry, especially in physics where mathematics is the language that allows you to write physics. You do lots of symbolic computation. And so your physics professors want you to be able to work well with the numbers and the symbols. So again, maybe like the tanker problem, not earth-shattering, but certainly a good example of using factoring techniques. Now, what I want to do is to look at a factoring technique called Professor Ron's AC lemma. Now, when it comes to factoring trinomials, most of you already have a technique for that, so I'm not trying to give you a new technique. I'm just trying to offer you something that will help to amplify what you already know. And many students in pre-calculus find that this is a unique way to actually think about factoring trinomials that is easy to teach. So let's look at this. So Professor Ron's AC lemma. So what we want to do is review factoring trinomials. So now the first thing I want to say is I just want to give you a recipe. And if you want to work into more detail with this, studying it, you can. I won't hold you responsible for this. There will be some theoretical constructs that I will want you to know. But here's what we're going to do. So we're going to say let P of X, just as a polynomial, we could call it F of X, be quadratic or even have quadratic form, ax squared plus bx plus c, where we're going to say that a, b, and c are integers. And one of our symbols for integers, the set of integers, is the German z. That'll be something I'll use. Right now, I'll just say are integers. We could say elements of z. And the greatest common divisor, GCD, of A, B, and C is 1. So basically here, we're going to assume that the A, B, and C are non-zero. Otherwise, you don't really need a fancy factoring formula for a trinomial. Certainly, if the B term is 0, then there's not, you just, you can either factor it as a difference of squares or factor it with imaginary zeros. So that's not difficult for us. So we will make these assumptions here. Now, when it comes to factoring, for instance, an integer polynomial, that is, when would we know that this integer polynomial could be factored over the integers or in the integers, so to speak? That is, we could write this as the product of two first degree integer polynomials. So we will say the following: P of X can be factored in z of x. And this is what I'm going to say for polynomials. I'm going to use z for integers and bracket x for the polynomials. So basically, when we use, Professor Ron uses this symbol here, we mean integer polynomials. Lots of times in WebAssign, they'll say, make sure you have an integer polynomial. We always have to follow the formatting instructions in WebAssign. It keeps us on our toes. That's one reason I like it. It will definitely make you better, but it will sometimes be a thorn in your side. That's just unfortunate about math, but it does make you better. So P of X can be factored in Z of X, the integer polynomials. So that means we could break this down to the product of two first degree integer polynomials, if and only if. And here's the recipe. There exist integers z and w such that, and here are the two recipes. Number one, A times C, this is why we call it Professor Ron's AC lemma. A times C equals Z times W. And B is actually the sum of Z and W. So we have, this is a theorem that we work in reverse. So, and I'm sure that you have seen this before. Let me just, I'll come back to this. Here we go. I'm sure you have seen this before in some form or fashion. It's just that, oh, I lost my, I always like to try new things and then I lose my screen. There we go. All right. The thing is that I am sure you have seen this before in some form, maybe not written this way, where you basically drew a little box to figure out factors. And I've seen many students utilize that this is what we're stating right here. Now, when you look at an example like this, and you think about doing a problem like this, you're thinking, okay, well, maybe I can try this by trial and error, or maybe the numbers are kind of small or large. I'll just try looking at the discriminant and, you know, hook or crook kind of thing. But what's nice about this is that when you need factorization, it is a nice technique that cuts down on the trial and error. There is a trial and error part, but it's very sustainable, so to speak. So here's an example of this. And then you might be thinking, are the Z and the W unique? Well, the idea is that it doesn't matter about the assignment, but once you find a Z and a W, accepting the order, you do get a uniqueness. So the thing is, in algebra, there's a very famous theorem called Gauss's theorem that says polynomials that factor over the rationals automatically factor over the integers. And that's really the result we're using here. So here's an example. Let's just say we have 6x squared plus 11x minus 21. And with this, we're also going to use zero product just to practice solving equations too, just to as an extra piece in the detail here. So what we want to do here is to factor in z of x. That is, lots of times in WebAssign, you know, students will say, well, is it prime? I can't factor it in the rationals. You know, usually when WebAssign asks you to factor something, it can be factored. And so in this particular case, what we want to do is apply the AC method and see if we can actually factor this as a product of two integer polynomials of degree 1. So let's use the AC lemma, or the AC, Professor Ron's AC lemma. AC, in this case, is 6 times the negative 21. Now, first, we can look at this and say, well, okay, if we add these two numbers here, notice we get a negative 15, and that's not an 11. So as it's written, maybe this isn't working out very well. So what we can do is we can think of factoring. So we have a 6, and then we can look at maybe a negative 7 and a 3. And then when you look at this, you're thinking, okay, well, you know, this doesn't look half bad. This actually is a big improvement. Notice here with the negative 21 written as a negative 7 times a 3, this allows us a way to actually get to that 11. And again, you don't have to, you know, you don't have to work through this. Maybe you look at this in a little bit different way and you come about it through other means. But the result will be that we will come up with a Z and a W. Notice here, the 3 times the 6 will give us the 18. And if we subtract 7 from the 18, we do get the 11 here. So this would be a way to write a Z and a W. So now we can just say, let's just put these two together, and this will give us an 18 times a negative 7. Now, the nice thing about this is that once we find the Z and the W, we can rewrite the middle term and factor by grouping, which again is easy to do. If we can factor by grouping, we don't need any fancy formulas, but unfortunately the factoring by grouping isn't always available to us. So now this is a check. If you like, we can call this the Z, the 18, and we can call the W the -7. It doesn't matter. So now we have 6x squared plus 18x minus 7x minus 21. Again, it doesn't matter the order you write these. You can now factor by grouping. And if we look at the first two, we can factor a 6x. And if we look at the last two, we can factor a -7. So we have 6x, x plus 3, and then we have a -7. So if you want, ladies and gentlemen, you can write this as a plus -7, and then just write x plus 3. The idea, if you have a z and a w, you will always get a common factor here. Again, that's the theory at work, the Gauss's theorem, which I quoted. Again, we can always use formulas, ladies and gentlemen, to write down this theorem, but most students find it much simpler just to do this. Formulas may be difficult to remember and may be awkward, depending on the type of problem you're doing. So this type of technique is very nice. And of course, this will work, ladies and gentlemen, for any quadratic polynomial or polynomial in quadratic form. So again, this is a very powerful technique. Though it doesn't solve everything, it certainly solves quite a bit. And so now we can factor. So we have 6x minus 7, and then we have x plus 3. So now when you look at this and you think, okay, well, this would be a method for solving equations. Because if you had to actually solve this, that is, if this equation were presented in a way that defined the zeros of the polynomial, or to solve the equation 6x squared plus 11x minus 21 equals 0, this factorization would be very useful. So we could say 6x squared plus 11x minus 21 equals 0 if and only if. Now we can use zero product. Again, if a product of factors, complex factors, is equal to 0, then it must be the case that at least one of the factors is 0. Otherwise, you would not get 0. So this would say 6x minus 7 equals 0, or x plus 3 equals 0. So the factoring technique you already know from Algebra 2 and college algebra to be extremely important, and sometimes the only way to find solutions. We are definitely not filled to the brim with all kinds of nice factoring formulas. You know, rational zeros theorem, which we will review, when it works is terrific, but boy, when it comes to solving polynomials in general, we have to usually work very hard. So now notice we can easily solve this. We have 6x equals 7 if we add 7 to both sides, and then divide by 6. And then, of course, we can just subtract 3, so x equals -3. And so now when you look at this, you can say we have a solution set of 7, 6, -3. Again, in WebAssign, you'll usually type your responses separated by commas. And again, what's very important is that in mathematics, we will always assume the exact answer. We will always assume the exact answer unless WebAssign requests an approximation. For instance, If the answer is 1/2 and you put 0.5, that's fine. 0.5 and 1/2 are equivalent. There's no approximation there. But if, for instance, an approximation were requested in WebAssign, say you were doing a radioactive decay problem or something like that, they would say, well, please round your answer to a certain number of decimal places. So just as a word to the wise, unless the problem requires an approximation, you are not required to do that. You are required to give the exact answer. So there'll be times when you'll fall into this trap, and that's just a matter of getting used to writing mathematics. But if the answer is the square root of 2, then you use your little symbol palette and you put square root and a 2 as the radicand. Again, always remember that we are interested in the exact response unless WebAssign instructs us to do something different. So again, factoring here, again, the Professor Ron A.C. lemma. This is just maybe a different way of stating the theorem that you have used many, many times already. So this is not giving you really anything new. Maybe it's just giving you a different way to look at it and maybe make it just a little bit simpler when it comes to explaining this to friends. I think it's important about the statement of this theorem that it's really easy to describe. And if you have friends that struggle with factoring, then you can help them with this. Now, one thing that I wanted to mention about is just a simple factoring technique. Often, when it comes to working with polynomials, we like to have a list of rules, a list of tricks that, well, you know, that didn't work, this didn't work, are we just stuck? We can't factor by grouping. But what I've done is I've assembled some examples where you can actually fix a quadratic form polynomial of degree 4 to actually make it factorable. And again, this is a technique that the WebAssign introduces that I think is interesting. So here's an example. For instance, consider the quadratic polynomial, of degree 4. Now you're thinking quadratic, well, it has quadratic form, okay? And so here's an example. X to the 4th plus 4x squared plus 16. Okay, now when I say quadratic polynomial, it's quadratic in x squared because you have x squared squared plus 4 times x squared plus 16. So this is a quadratic polynomial of degree 4. So we say quadratic in x squared. Now, when you look at this and you're thinking factor, so here's what WebAssign is asking you to do. Factor as a product of 2 degree 2 polynomials. Factor as a product of 2, and I'll just say 2 degree polynomials. And you're thinking, okay, so we're going to break this 4th degree polynomial, which is actually quadratic in x squared, to a product of 2 degree polynomials. So the thing is that instead of trying to be more generalized, we can look at this and say, well, first, if you look at this and think, oh, okay, well, if I had to solve this equation, maybe we're in theory of equations, you look at this and say, well, there's a 16 there, that's x to the fourth, and that's 4x squared. You're thinking, well, I can't get zero out of this. I mean, there will not be any real zeros here. So this is actually a theory of equations problem. It would be impossible to have any real number that would make this zero. So if you were thinking, that this was kind of down the road as a question about what are the actual zeros, then you might be thinking, well, I know they're not real because I can't add non-negative numbers to 16 and ever get zero. So what you want to do is think the perfect square. So remember, with the perfect square, this is where these factoring formulas are useful. Perfect square. We'll take whatever we can get. The perfect square, for instance, in the fourth degree would look something like this. X to the fourth plus 2, I'll just use a beta, 2 beta x plus beta squared. Because if you looked at this would just be x squared plus beta squared. X to the fourth, beta squared, and then x squared times beta times the 2. Oh, and I need a square here. So you're thinking, if I can rig this so that it looks like this and then subtract the part that I added, that would make not only the perfect square, but it would make a difference of 2 squares. So you're thinking, oh, okay, so this is really a trick. So what we're noticing here is that this example here is basically derived from the first list that we had. And so we could mimic this here. And if we think about this, okay, well, there's the beta squared, that's the 4 squared. So let's rewrite this so we get the 2. So now equivalently, x to the fourth plus 2 times 4x squared plus 4 squared. Now this looks just like this. X to the fourth, 2, we see the beta is 4, x squared, and then beta squared, all right? So the thing about this is that you don't have to memorize this, you just have to see, oh, this is manipulating the difference of 2 squares once we get the perfect square. Now, if we have an additional copy here of 4x squared, we have to subtract. So this equals, I'll just put equals here. This equals this as long as we subtract the additional copy of 4x squared. So here gives us 1 copy of 4x squared. We add an additional copy to make the perfect square here, but then of course we pay for it here. So now let's use the formula. So this will be x squared plus beta. So we have x squared plus 4 quantity squared. And then of course we can write this as a perfect square. This would just be 2x quantity squared. It's kind of simple. You don't have to work too hard for this. And you could do this where you get a radical here if the 4 weren't a perfect square. It wouldn't matter. It just wouldn't look as pretty. You just have coefficients that were irrational numbers. And so now you're thinking the original problem is now written as a difference of 2 squares. And now we're back to the mode area, unmode area problem. So this will give us x squared plus 4 minus 2x times x squared plus 4 plus 2x. And if you want to write things in descending order, this will be x squared minus 2x plus 4, x squared plus 2x plus 4. So now when you look at this, you're thinking, wow, look what we did. We now factored the quadratic polynomial of degree 4. That is, this has quadratic form. That's why this works at all. And so we've written this, we factor as a product of two degree polynomials, two degree. Okay, but now these are both quadratics, which we understand, and these actually have imaginary zeros. So we could use the quadratic formula on this. We're going to say more about the quadratic formula clearly, but what I want to show you here is that if you were working on a problem in physics, or you're working on a problem in pre-cal or calculus, and you're thinking, well, you know, I don't even have to worry about factoring this because it has, you know, clearly doesn't have real zeros. And in calculus, we usually just deal with real numbers. But you might be in a physics situation where these imaginary zeros are actually quite important. You're going to find sometimes when you do engineering problems that you have to understand the imaginary solutions to understand the real solutions. So one nice thing about complex variables and complex analysis is that it actually helps us to understand real analysis more. Even though that seems a little bit crazy, it's actually very true. So now what you can see, and when you practice your WebAssign, they go through a little summary about what I've done here. I've given you more detail because I don't want you to think it's just smoke and mirrors. The idea is that you're actually utilizing the formula for the perfect square, make the perfect square and then adjust for it. Then you have two formulas here that can now be combined as a difference of two squares. And again, that formula allows you to go from here to here and then just neaten it up in the descending order. So we can get a factorization of this by using a fairly simple technique by creating the perfect square here. So this is where understanding some of the really basic factoring formulas can be extremely helpful. And the thing is that maybe this isn't a far-reaching factoring example, and it is limited in its scope. But the nice thing about it is when you think about the fact that if you're working on an example and this gets you from point A to point B successfully, then it's a good thing. The one thing about mathematics, it's almost like reading history. Every time you read something new, you have a different way of looking at things. Your perspective changes. And even though mathematics is exact, coming up with good solutions and good techniques can be anything but simple. Okay, so here's a really nice example of how you can create a nice factoring problem just by utilizing the perfect square. And I encourage you to look at the WebAssign problem here to practice this. And notice that in the problem, they'll give you some simple ones that you can factor by grouping that you don't need this technique to do. So it's not always the case that you have to take out the larger artillery to do this. Now, techniques in factoring and all, we'll continue to do more of. And as we work through the course, we'll review factoring. Now, one thing I wanted to talk about are some rational expressions. Again, oftentimes when we're solving equations, we often have what we call fractions with variable denominators, and we clear the denominators to figure out any real solutions or even maybe imaginary solutions just by bringing all of the algebra into the numerator. So before I do that, I just want to review some very simple constructs about dealing with fractions. Fractions tend to be things that we always run away from, not because we don't understand them. We just don't want to take the time to understand all the nuances of fractions. A word to the wise, don't shortcut fractions. Always do all of the due diligence and make sure that you can justify all of the steps that you do, because when you make careless mistakes with fractions, it really does put a wrench into the problem. So here's an example. What we want to do now is just to simplify the fraction. So simplify by performing fractional division. So this is again another practice section in your WebAssign that may be a little bit dry, but very useful. So we have x plus 1 divided by 25x squared minus 16, of course, our friend, our difference of two squares, divided by, we have x squared plus 3x plus 2. And then we have 5x squared plus 21x minus 20. Now, when you look at this, this is just the definition of division. So for instance, remember, if we have A divided A over B divided by C over D, we just invert and multiply. So this is AB times D over C. That's just the definition of division. Again, nothing difficult here. Let me go ahead and, there we go, get a focus a little bit. So when we think about this, the first thing we can do is go ahead and get rid of the division symbol. Again, we could write this as a compound fraction, a fraction divided by a fraction, but you sometimes see the division symbol too. So we need to be able to work with that. I mean, again, this could also be written as A over B divided by C over D. And of course, this would be equal to this also. This would just be using a fraction bar here in place of the division symbol. This occurs often too, especially in physics and mathematics. So now we can say x plus 1, 25, x squared minus 16 times 5x squared plus 21x minus 20, and then x squared plus 3x plus 2. Okay, now at this point, you're thinking, well, what we want to try to do is maybe use the AC lemma and factor and see if we get some common factors. Again, we've got a difference of two squares here, and we can easily factor that. But let's just go ahead and notice that this is a simple factorization. We can use an x plus 1 and an x plus 2. That's easy. But notice here, let's see if AC will work in the numerator here. So let's just go ahead and test to the side. So we have AC equals 5 times a negative 20. Now, of course, when you look at this, you're thinking, okay, this isn't so bad because we just need a 21. And then, of course, the 20 can be written as 5 times the negative 4. So this will give us a 5 times a 5, and then the negative 4. So that'll give us what we need, because the sum here, if this is the Z and the W, then we can see that the sum of the Z and the W is 21. And by Professor Ron's AC lemma, that means that this will factor in the integers as the product of two first-degree integer polynomials. So now let's go ahead and use that. And here, of course, this is easy and this is easy, but this just took a little extra step here. So we have x plus 1 and then we have the 5x minus 4, 5x plus 4, and now, of course, here we can go ahead and write in, we have 5x squared plus 25x minus 4x minus 20, rewriting the middle term. And then, of course, this was the easy factoring, x plus 1 times x plus 2. Well, when it's easy, and we certainly aren't going to argue with that. But of course, we had to do a little more work here. And so now we have x plus 1 and we have 5x minus 4, 5x plus 4. And here we can factor the 5x. So we have 5x times x plus 5. And now, of course, we can factor the negative 4 and get another x plus 5. And then, of course, x plus 1 times x plus 2. Now, we can finish by factoring by the grouping. So we have x plus 1, 5x minus 4, 5x plus 4, and then we have 5x minus 4 right here, and then an x plus 5, and then, of course, downstairs, x plus 1, x plus 2. And now we've reduced everything to products of binomials. And notice we can always box common factors. Probably not good to put slash lines through them, just kind of notate, put a little check by them that they absorb. And then, of course, the 5x minus the 4 and the 5x minus 4 here absorb. These are what we call functions with holes in them. That is, they don't define vertical asymptotes. They just define problems, so to speak. They basically just define holes in functions. The function does not become infinite or unbounded, and that'll be something you're going to say more about in this class, and also discuss more intently in calculus when you talk about infinite limits. So again, we jump into calculus before we formally define calculus. I guess that's what pre-calculus is all about. And so what's left will be the x plus 5, and then 5x plus 4, and then x plus 2. Again, this was just a little practice example, not very difficult, but just to give you some review on how we work with expressions that have to do with fractions. Now, one thing that actually comes up quite often, sometimes students have to factor and you're not necessarily following anything, but maybe getting common denominators, collecting terms and cleaning things up, maybe getting rid of negative powers. Usually when it comes to solving equations, for instance, if this were a calculus problem, we would certainly see if this were basically where we were starting at this point, this would be a nice rational function. We can see that the degree in the numerator is 1, the degree in the denominator is 2. We can certainly know when it would be equal to 0. We would certainly know the definition of vertical asymptotes. So the idea is, as we work an example, we just want to make sure that as we work through it, we keep track of what we did to get to this point. So oftentimes when it comes to working physics and mathematics problems, we have to remember, the actual steps so that we don't make assumptions about the expression that we somehow forgot in a previous step. So what's important here is think about what the problem says, think about what it means, and how you move forward from there. Even though this is just a nice practice problem dealing with the definition of division, we certainly get a lot of practice thinking about functions with holes in them and vertical asymptotes. Now, one example that makes its way into working with rational expressions that you're going to see in calculus. Again, what Dr. Stewart does, ladies and gentlemen, is that he just throws these problems in. You're not doing the actual differentiation, you're just doing the algebraic part that you learned in classes previous to calculus. So here's an example, kind of like what we did with the last problem. Say we have 7 minus 3x to the 1/2 power, a square root, plus 3/2 times x times 7 minus 3x to the negative 1/2 divided by 7 minus 3x. And there are lots of examples with this where you get to practice with this type of technique. Now, for instance, maybe you did some calculus or you did some type of operation and the result was this fraction. And you've got a fraction within a fraction, so to speak, because what you might want to do is maybe find out, is it true that this particular expression could be 0? And if it could be 0, what is that 0? So what you can do, and this is where I tell students you have plenty of flexibility here. One technique I like to teach is that when you have a particular base, so to speak, you can always try to factor the least power of the base to clean up things and then move negative powers into the denominator to eradicate them. Now, what we can do here, and this is your choice, it's not certainly the only way to do this, we could factor the 1/2 and we could factor the least power of 7 minus 3x. So we've got 1/2, and then we have the least power of 7 minus 3x, which is the negative 1/2 power. And remember, downstairs, we have a 7 minus 3x that's just living there. And so, of course, here, if we factor the negative 1/2, we have to pay for this by writing as a 2 times 7 minus 3x. Notice if we factor the 1/2 here, then we've got to pay for that 1/2 with the 2. And then, of course, the negative 1/2 here, we have to pay for that by putting the 1 here. So when we add the 1 and the negative 1/2, we get 1/2. So if you want, you could just put a little 1 there. And then now what's left? Well, we factored all of this stuff. The only thing that's left is the plus 3x. Let me put that a little bit closer. So this is not difficult, and it's certainly not the only way to do it. You could take this downstairs and get a common denominator and then get the exact same thing. This hopefully might be just a little bit more efficient. So again, don't always check when you multiply back through, you get the 1/2, the 3x here, and you get the negative 1/2 power of the 7 minus 3x. That's a check. When you multiply here, you get the 1 plus the negative 1/2 gives you the 1/2 power, and then of course the 2's and the 1/2's absorb. So these are equivalent. Now what you can do is you can bring the 1/2 and the negative 1/2 power of 7 minus 3x into the denominator. So, and then of course simplify here. So this is going to give you a 2 times a 7, which is a 4, minus a 2 times a negative 3x, which is a negative 6x, plus 3x. And then of course we'll have the 2, and then we'll have the 7 minus 3x. In this case, now notice, if you like, just to make it a little bit simpler, just put the 1 there. So the 1 plus the 1/2 will be the 3/2. Sometimes it's a little bit easier if you just go ahead and put 1 so you don't forget them. And so now notice we have a 14 minus a 3x. And then of course downstairs we have 2 times 7 minus 3x to the 3/2. Now, what I wanted to mention here is that if this were a calculus problem, it would be very simple to actually now find zeros. You could factor this if you wanted it. This is fine the way it's written. If you wanted to factor a negative 3, you'd have an x minus a 14 over 3. And we have a 2 times a 7 minus 3x to the 3/2. Now again, this is saying the same thing, but now we can easily see that the 0 is 14 over 3 here, 14 over 3. And of course, this is in the domain here. 14 over 3 certainly doesn't make 7 minus 3x 0. So the idea here is that by cleaning up the algebra, you can now see that this expression can be 0. And maybe you would be uncovering what we call a horizontal tangent, where the tangent line was actually horizontal to the graph of the function at that point. So the idea here is that even though sometimes when you're doing some of this factoring in the WebAssign, you're like, why are we doing this? This is just kind of like busy work. And maybe it is, I'll agree with you, but it's important busy work. And it'll be things that you'll need to be able to navigate when you get to calculus. Remember, pre-calculus is to prepare you for calculus. So there might be things that we're doing that just seem a little odd, but don't look at it that way. Think about this as building your foundation so that you're really good at what you're doing. Sorry, I got confused. Where did the, oh, okay, I can do that. Let's see here. Now, we're saying the 2, and we got the 7 minus 3x to the 3/2. Okay, notice here, everybody, this is a good example. Notice here we've got the 1/2, and we have the 7 minus 3x to the negative 1/2. Okay, what I want to do is to take that part and just move it into the denominator. So I'm going to add an extra step here. So I'm going to go ahead and write this as 14 minus 6x plus 3x. And now let me just go ahead and move this downstairs. So the 1/2 will just be 1 over 2. So do that. And then bring this downstairs. That'll be 7 minus 3x to the 1/2. That is just writing the 1/2 is 1 over 2. And then the 7 minus 3x to the negative 1/2 downstairs is 7 minus 3x to the 1/2. And remember, the 7 minus 3x to the 1 is already there. And that's good. That's an excellent question. Now notice the 2 is here, and then we can add the 1/2 and the 1 and get the 3/2. Is that better? Is that more steps there? This is really important. So just think about it. Think about when we have a setup like this. Excellent. Thank you. Very good. Very good. I'm glad you all use the chat, because I always do look for it, and I want to make sure that all of this makes sense. This is what I was saying before. When you work through these problems, don't do what I did and combine too many steps, break down all the steps and then add the powers here. And then you can see that the simple is better. Okay? Excellent, excellent. So I'll just say good questions. Oh, got to move my keyboard. Excellent. Now, one thing that we want to be able to do when we talk about, and here's another thing too, ladies and gentlemen, as you work through these examples, don't look at this as anything but preparation, even though it seems like we're just kind of doing a little bit of this and a little bit of that. You'll be grateful that we did this. It's one reason I used the Stewart pre-cal book, because Dr. Stewart, even though God rest his soul, he passed away last year, his colleagues in his book, I think, is one of the finest examples of preparation for pre-cal. There is no perfect book out there, but this book does give you plenty of rigorous examples and problems to get you ready for the calculus. Because when you take calculus, I want you to be confident and I want you to feel good about what you're doing. Now, one thing that we want to talk about is just some simple properties with solving equations, and then do a simple example. And then we'll continue with this at our next class on Thursday, ladies and gentlemen. So the first thing is, I'll just say, solving more equations. So let's look at this example. Here's the first one. We've already talked about this zero product, but this is called the square root property. Now, I'm sure you talked about this in algebra 1, or excuse me, algebra 2 and college algebra, but let's just say this. At this point, let A be a real number. And here's a new notation that I don't think I've used yet. I'll say the little e here, the little epsilon, that means element of, and then the R here, like we use Z for integers, this will be real number. Real number. So when we do the script R, that means A is a real number. And in this particular case, we're going to call this fixed. Fixed. We say it's fixed, it's a constant. That is, so for some fixed real number A. Then we can say that x squared equals A is equivalent to, that is, the real numbers are very, just like the complex numbers, have really interesting properties. So if we have the square of some real number equal to a fixed real number, what does that say about x? Well, it says that x is either plus or minus the square root of A. This says x equals plus or minus the square root of A. This is what we call the square root property. And it doesn't mean that you put square roots on everything until you solve for x. One thing that students suffer with this particular theorem is that they try to put in too many square roots. So for instance, if you had something like this, so here's a simple example. Say you have x squared minus 75 equals 0. And you're going to say, okay, well, I can use the square root property. So that'll be equivalently x squared equals 75 And then that would say x equals plus or minus the square root. And while we're at it, 75 is just 3 times 25. So equivalently, x equals plus or minus 5 times the square root of 3, since the square root of 25 is 5. So again, you're thinking, there's a quadratic equation, Professor Ron, and it is, but it's a very simple one. And of course, this x can be any expression, any real expression also, even complex expressions. The idea here is that this allows us to move to the solution very quickly because we have the absence of the x term. Okay, so this is very important, very simple, but extremely important. And the plus and minus is very, very important, as you well know. Oh yeah, x squared equals 25. Well, then the answer is plus or minus 5. So always remember the statement of the square root property as being very simple, and you want to move from here to here. That is, if you want to start with, and then you might be thinking, why is this even true? Well, let's just see why it's true. For instance, we'll say why, because we can factor. So if we start with x squared equals a, you're thinking we could have thought of the proof here, but we're not going to do the proof every time unless we just need to factor things. So we can say, well, this equals this, but this is x squared minus a. And then you think, okay, well, we can use properties of absolute value, or we can use difference of two squares. We can write a as the square root of a squared. Or excuse me, we can write a as the square, of the square root of a. Not, I don't want the absolute value yet. We can write it this way. Later on, I'll say what I said initially. That'll be the definition of absolute value. So what we can do is we can take the a. This is like saying something like this. This is like saying 3 equals the square root of 3 quantity squared. That's an identity. The 1/2 and the 2 absorb. And so we can take the real number a and we can write it this way. And of course, we could, the square root of a could be an imaginary number. That's okay, no problem. So now we look at this and say, well, this is just like the factoring technique I taught you. This is a difference of squares. So then equivalently, we see factoring is so important. X minus square root a, x plus square root a. I mean, we clearly don't want to have to do this every time unless we're doing a problem where we're trying to do a complete factorization, where this would be very useful. But at least in terms of solving equations, it's great to be able to go from here to here kind of quickly. But now this is what I've already talked about before, the zero product. So if I've got the product of two expressions in x, two real expressions equal to 0, then it must be the case that at least one of these factors is 0. So that's the zero product. So equivalently, x minus the square root of a equals 0, or x plus the square root of a equals 0. But now, of course, that means we can solve for x. So x will equal the square root of a, or x equals the negative square root of a. So again, when we go from here to here, we're leaving out all these intermediate steps. It doesn't mean that they're unimportant. You just don't have to do this every time. I don't want you to have to do it. Again, unless we're doing a factorization of a polynomial and we need to see all of these linear factors, so to speak. where we showcase all the zeros. That's a technique that we'll see again as a review from your college algebra. But now we can see we can combine this. So x equals the square root of a, or x equals the negative square root of a. So this is the punchline, so to speak. X equals plus or minus the square root of a. So what we see here is that we can go from here to here in the statement of the theorem, but of course that requires filling in all these details, but we don't have to do that every time. It might just be comforting to know that when it comes to the square root property, once we have it, we can go from here to here quickly, and that cuts down on a lot of work. Again, I want to focus on the fact that sometimes it's convenient to write equations this way, especially if we're looking for complete factorization, and that's a different type of problem. Or if we're trying to figure out the zeros, or an inequality where something may be positive or something may be negative. It's often interesting to be able to find the boundary value, so to speak. So unfortunately, when it comes to doing pre-cal, we do a lot of review from the college algebra, and that may be a little bit dry, but I want you to get into that routine of doing as much practice with the math as you can. So by the time we finish the review and we hit the trigonometry, you'll be in a good study mode, because trigonometry will be tricky because some of it will be new. And I don't want you to be into a funk as far as studying. I want you to study all of this like it's new, so that when we hit that trig and some of the more new topics, you hit the ground running and you know what you need to do. Now, like I say, for the Blackboard, and this is really important. Let me just go back to that and share that screen. When you look at the Blackboard, of course, I'm always going to put notes here and give you announcements about things that we need, especially where we have our Zoom. And we'll also have conference hours with Zoom. I'll send out email invitations for that. Now, one nice thing here is about the WebAssign. You can always access the WebAssign from the Blackboard. Now, of course, if the Blackboard is down for some reason, you can always access WebAssign directly. But if you've used WebAssign before, then you can use old username and password. If not, you can just set one up. But when you click on the WebAssign, it takes you directly to the WebAssign page. And what this does is just give me classes that I'm teaching this semester. And so you will have the classes that you have. And of course, with all the WebAssign, there will be the due dates for homework assignments and quizzes. So that should always be very clear to you. You'll always have into the next week to actually get the assignments done. So for instance, here, if we go back to Blackboard with the assignments here for week 1, you can see here that it says complete quiz 1. Well, that means you're starting to think about that. It won't be due until the next week, but this tells you about things that you need to be doing during the week. And then, of course, it gives you a way just to check to make sure you've gotten everything done. One nice thing about the virtual setting is that you always have the lecture, which supports your understanding. Many students are, every student is different. Some of you love the lecture. Some of you like to be completely independent. And I don't want you to worry about that at all. I want you to use whatever techniques work for you. But notice here with the lecture recordings, every time we do a lecture, I will post the lecture so you can use that for future reference. So I want to thank you for your attendance today. Like I say, I will be sending out email invitations for conference hours, and we will meet every Tuesday and Thursday at 8:10 to 10 o'clock for our virtual class. So thank you for your attendance today. and I wish you well as you begin this class. And please take advantage of the conference hours. They are for you. I've got several conference hours all spread out through Monday to Friday, even some in the evening to accommodate crazy schedules, because I know your schedules can be different because you have jobs and you have responsibilities with your families and all. So please look at the syllabus to check out the times for that so that you can take advantage of a time that works best for you. Well, everybody have a great day. And if I don't see you at the conference hours, I'll see you at our next lecture. Everybody be well, drink plenty of water. Bye.
Um, can I make a question?
Sure.
Oh, okay. So why is it important that the common divisor is 1 in your lemma? What happens
which
if it's
one?
not?
Oh, which one is that for the square root property?
Yeah, for let p of x be ax squared plus bx plus
Oh,
c.
let me get that. Yeah, let
Yeah,
me pull that
please.
back up. Here, let me pull this back up. So let's see. Right here.
Yeah, that
Okay.
one.
What was your question?
Why is it important that the only divisor between a, b, and c is 1? What happens if it's not?
Oh, that's fine. All this is saying is that if you have extra stuff, then you can get rid of it. For instance, look at the example that we did. I'll show you something that'll cut down on the amount of work. Let me find that example that I did. Oh, right here. Say for instance, all of this was multiplied by 2, and you had 12x squared plus 22x minus 42. Okay. All of this extra stuff you don't need. That you've got a factor of 2 in all of this. So I don't want you to deal with extra factors that make the problem harder, because see, all this common factor is not going to change the factorization. So you could say 2 6x squared plus 11x minus 21 and factor that way and still focus on this. You'll still have a 2 here, okay? But the thing is that when you work with the smaller numbers, it's so much easier to have them relatively prime. You could ignore this, but you do a lot more work. That makes sense?
Okay, yeah, it does. Really, it does.
Oh, absolutely. Of course it does. The thing is, Gabriella, is that lots of times when it comes to doing math, I don't want you, for instance, you're thinking if we factor this, the 2's there, but if we're solving for zeros, the 2's not going to make any difference at all. But I don't want you to forget about it. I just want to make sure that when you factor, that you pull out all of the common factors and make these numbers as small as they can be. Now, again, like I say, that's just a way to ease the amount of arithmetic, but that's an excellent question. See, that's really good because that means you're paying attention. So you get 10 points.
Aren't those restrictions? Like
What?
where ABC are integers, z and the greatest common denominator ABC equals 1. Aren't those kind of like restrictions for the problem?
Well, it's just basically saying that when this is called a hypothesis, it's basically saying that when you work on this, you want to get rid of all the extra stuff and just focus on the ABC that are all relatively prime. That's called a hypothesis, not necessarily a restriction, but yes, that's in a way, yes.
Okay.
But here's the thing, Jeremy and Gabriella, the idea is that we want to make the numbers as small as possible. And so if we can make them smaller, maybe we work a little bit easier. That's all.
Okay then.
Okay, yeah. And so Z and W exist. Are they unique?
No, what I was saying, like when we look here, see, I could let my Z be -7 and the W be 18. as far as the order goes, they're not unique, but accepting the order they are.
Oh, okay, very good.
So
Yeah.
if you assign Z to be -7 and W to be 18, it's not going to change the factorization. It's just going to mean that that's how you decided to label your Z and W. Except for the order, they are unique. Absolutely.
Very good.
This is
Thank you
a
so much. Yeah.
Well, you're welcome. This is my own lemma. I devised this when I was teaching the honors section of this class. I devised this theorem, and the proof is not very easy, but I wanted to give you a statement of it, ladies and gentlemen, that would give you some understanding aside from what you already know. And now what I want you to do is I want you to take this theorem and share it with your friends and show them how to factor using the AC lemma. They might be amazed. And then they're going to say, you're so smart. So yeah, it'll be something that'll add to what you already know.
And one more question, sorry. So can it be proven with just what's it called? Yeah, with just knowing well, just using the hypothesis, or do you need like more stuff?
Well, for instance, when you're actually writing down the factorization, going from this direction to here is pretty straightforward, but starting here and going the other direction actually requires more fancy factoring and the use of Gauss's lemma, but it's very doable. It just, this direction going here to there is a little bit harder, but you should try it. First, what I would say is start with this side and go to 1 and 2. Try that first, and then try the other side.
Okay, I'll try the
You,
easy
you,
one
mi-
first.
you might be amazed at how simple the first one is, but again, just follow everything the way it is. But then once you get good with that, try the other direction, and I'll be glad to say more about it. But that we can do during maybe office hours.
So
All right.
one question I have is, so a lot of people are asking where we can find the recordings of this, because I missed
Oh.
like the first.
Oh, that's fine. Once we're done with this, I will get a Zoom recording, and then it will download to me, and then I will go to YouTube and format everything, and then once that's completed, over here on the let me just do this first. Let me share. And what I'll do is, right now we'll have lecture recordings, and I will, when you click on this, there'll be a week 1, and I'll put the content item there, and you'll have access the link to the lecture. And I'll do that every time. But that'll take me into the afternoon before I can post it. But it'll be up every day when we have a lecture. Absolutely.
Okay, thank you.
You're welcome. Okay, now everybody, I'm going to send out email invitations for the conference hours, but do me a favor, make sure that your Sanjak email is functioning. That is, you actually use it and that it works, because I'm going to use your Sanjak email to send the conference hour invites. Okay, so make sure that email is working. I know most of you have functioning emails, but you don't always like to use your Sanjak email for correspondence with your friends, but I'll always try to communicate with you through the Sanjak email. Okay, so I appreciate your questions, and I look forward to seeing you all at the next lecture, if not the next lecture, at the conference hour. So everybody have a great day.
Have a great day.
Thanks, everyone. Oh, and Gabriella, do you want to be a math major?
Sorry.
Do you want to be a math major? Because you seem really intent with the math.
Oh, well, so in Mexico City, I did, I was a math major. I am still, I'm about to finish my
Oh.
bachelor's in math, but well, math is hard, so
Oh,
it's taken me a while.
But it's so rewarding. It's so rewarding, and you seem to really like it. So that's really great. That you'll enjoy this class.
Oh yeah, I am. And so that's why I'm interested in the theorem. But you know, like proving theorems, it's hard. I mean, like I still don't really get the hang of it. But yeah, right now in San Jack, I'm focusing on maybe doing engineering. So
Oh, wonderful, wonderful. Yes, you have a great career.
oh, thank you. And I'm actually in computer science, but I think I'm gonna change. And I took the class with Wiggins.
Yes,
And
yes.
yeah, and he told me, oh, take the class with you, and that's
Yeah.
why, yeah, I'm
Oh,
here.
Wiggins is wonderful, and he likes to teach the engineering when you know your math. So you will be his best friend if you do your math correctly.
Oh, okay, yeah. So he told me to take this path, to take class with you, and then tag along with in his classes too. And so here I am.
Absolutely. Well, that's wonderful, and I'm so glad that you're in the class, and it's great to hear about all the wonderful things you have going on. And if I don't, I'll probably see you at conference hours, so I'll see you later. All right.
All right, thank you. Bye bye.
Bye, everybody.